We talked about non-deterministic finite automata, deterministic finite automata, and how they can be used for finding strings in a larger text, finding patterns in a text. And you might remember this slide, and as many of you discovered, there were a few mistakes. Then I corrected them, and there were some mistakes left. So just to be clear, this is the final version. I'm not particularly using the NFA in anything except for motivation, so don't get too obsessed with the details here. But to tell the story again, we can start with an NFA, which is very easy to construct. And in theory, we can just transform any non-deterministic automaton into an equivalent deterministic one. And the DFA is the one that we would like to use because it's exactly the one that allows efficient string matching. Then there's, in principle, some problem lurking here that the state space could be much bigger, but it turns out it's not. And there's also a clever way how we can avoid the general construction. And here, there was another typo that I noticed last time, but it was end of the lecture anyways. So remember, we're looking at a pattern P, and we're trying to construct this deterministic finite automaton for matching the pattern in an inductive way. So we first computed for the first j characters, and suppose we call this entire automaton aj minus 1 because it goes up to j minus 1. It's easy to add the new matching transition. That's just this new one that goes out of state j to j plus 1 with this p of j. But then whenever we have a character that's not the next character in the pattern, we have to find the transition where that character should bring us. In the automata language, that's called delta j of c. That's the transition function. I'm in state j, and I read a c. Where should I go next? What's the new state? And by the definition of our automaton, we can write this as follows. It's the length of the longest prefix of what we've seen from the text. We've seen a prefix of the pattern, but then a new character that didn't match. We're looking for the longest prefix of that, which is also a suffix of the same thing if I delete the first character. Because I know I can't find a match of the same length. There was a mismatch, but I might find something that's a bit shorter. So imagine we have seen a part of the pattern, P0 up to J, and then we read a new character C, which is not the same as the next character in the pattern, so we cannot continue the current longest match. But we can take everything except this first character and try to find what's the longest match of this thing that I see here again. So I try to overlay this with itself. So that's the same word again, except that I shift it a bit, and it should match in all those positions where they overlap. We'll come back to these kinds of pictures today. So for now, that's just going by the definition what the state should mean. The state means I've seen a certain prefix of the pattern in the text up to now, and it's the longest such prefix. Well, because we've already constructed the automaton for this one shorter pattern, we can use that automaton to read that shorter part. So you just delete the first character of the pattern and start simulating the automaton from the start state, reading P1 up to Pj, and then the new character. That leads you to some state. We're guaranteed by the length of the thing that it will be one of the states that aj minus 1 already has, so that's well defined. And that will give you the answer for this new transition link. Okay? Now it seems, well, this is in principle fine. It seems that we would have to, for each state and each character, simulate the automaton from the beginning. That sounds fairly expensive. So it would mean m times sigma simulations of a smaller automaton, and each could take essentially m steps. But another clever insight is that you can avoid this by essentially keeping track of where you have been in the simulation when you go to the next character. The simulations that we use, in one step, if we add a new state, we will have to add transitions for all the different characters that we have, except for the one that's a match. But for all the characters, the thing that we simulate the automaton on differs only in the last character. So we already get a good step further if we simulate the automaton up to the second to last symbol and then only add the last step for each of the sigma minus 1 different new symbols. And the second interesting thing is if we do this for 1j and then go to the next state, we add the next character, we can keep track of that state. We don't have to simulate the automaton from the beginning, but we just add the next new state from this x. Okay? This way to explain how to construct the automata is shown in the video of Sedgwick, and I found that construction is so nicely illustrated, there's little use in me copying the presentation, so I'd rather show you the original. Now I don't know if I can get the audio. I can probably only get the mic or the audio. But I'll just try it with the built-in boxes. Oh, the HDMI. Let's try that. It's not very loud, is it? So we're trying to build the automaton for this pattern. And the video jumps right into the construction. So try to listen carefully.
Let's take a look at a demo of the full construction that came into DFA. So here goes, and again, I want to say for clarification step. Match transitions are easy, how we build those, and we're going to start at position 0, and the mismatch transitions are easy. So now when we move over, x is, when we're at position 1 of the pattern, x is where we would be if we started out without that character, which would be the empty string. So we start out with this one 0. For state 0, we do that without any further reason. So now we've got x initialized. So now what we need to do is fill in the mismatch transition for state 1. So what are they? They're what would happen if we found those characters and we were in state x. If we found an A, it would go to state 1. If we found a C, it would go to state 0. Maybe you notice that's just taking the entries corresponding to the entries we need from X's column and putting it in J's column. That's all it is. And then we need to update X, which is where it would be if we match the B. So it will stay in, X will stay in state 0. Now, let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, it's what would happen if we were in state X and we got a B or a C. So all we do is move those two zeros over to column 2. And then don't forget, we have to update X, and X goes where the machine will go if we saw an A to transition from 2 to 3. So we just move X to state 1. X in state 1, and we're doing position 3. And now you can see how really simple the algorithm is once it gets going. Now the mismatch transitions are A and C. That's what we have to fill in for column 3. But those mismatch transitions were already computed. That's where X would go. That's where it would go if we happen to be in state 1. So we move the 1 and 0 from column 1 over to column 3. And again, we update X. When we see a B, X goes to state 2. Again, you can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern with the first letter cut off. So it's supposed to be where you wind up if you got VAB. That's a check. All right, so now straightforward. State 4, we have to fill in B and C. We go to X's column and copy over B and C from X's column. Then we update X. Next is to C and A. We go to state 3. Now we're ready for state 5. We've got X all computed. And we need to do A and B, and we get those from X. So it's an A for 1, and B is for 4. It's just one to and then when we do the C, and the except this one, that's we do update X to get ready. But when we get to state 6, we're done. And again, just as a double check, X is where you be, which is B, A, B, A, B. That's the construction of the committee point at DFA.
All right. I hope you could hear what Bob was saying. I hope you could follow through. I'll just go to one of the interesting states again. The interesting point is you keep track of this state X, which is somewhere always behind the state J where you currently add new things. And whenever you're done copying transitions, you move J to the next state. That's always J goes to J plus 1. And X goes to some other state. It can jump back and forth. But it's always, in this case, if you go to the next state, if you go from J3 to J equals 4, you read the B. And that's why X goes from wherever 1 leads when you read a B. So 2 in that case. Okay? So you see this idea that you simulate the automaton you're currently constructing on the shorter pattern, but you don't always start simulating from the beginning and then read the same characters again and again, because it's always the same prefix that starts with P1 and then P2 and so on. So there's no need to redo that work. All right, that's how you construct the DFA. If you recall from last time, once you have the deterministic finite automaton constructed, searching for the pattern in the text is very simple. You start in the start state, and then you just simulate where the automaton goes by reading the next character from the text in each step. And if that ever takes you to this accepting state, you have found the first match. You can modify the automaton so that you can continue reading instead of stopping at the first match. That's a minor twist. So once you've done the automaton, you just need, for every character in the text, one table lookup to tell you where the next state is you should go to. That's essentially as fast as you can go. Building the automaton in the clever way we've seen means essentially just filling the table. M times sigma, that's M is the number of states and sigma is the number of different characters we can read. That's just the size of the output for the DFA. It's a table of size M times size M times sigma. That's the number of transitions we have. So the algorithm that computes this gets to fill out this table essentially in constant time per entry. So that gives you a total time of this for the string matching problem. and the space is immediately just the table of the DFA. So the good thing about string matching with DFA is the matching time is as fast as you can get. It's a single table lookup. It's also essentially best possible if you have a not too large alphabet, because you have to spend n plus m time. In the worst case, you would have to read at least every character in the pattern and read every character in the text to verify that there are all those matches that you report. The only thing that's a little of a downside of this method is the space overhead. If the pattern is very short and the alphabet is small, it's fine, but the alphabet might be all Unicode characters, and that's a few hundred thousands, and the pattern could be a few thousand characters long if it's an application in bioinformatics. So that would give you quite some space overhead for just the simple problem of finding one pattern, and we'll see better methods than that. Okay, that finishes the part on matching with the DFA.